And we're back. So I see we have a bunch of questions, so I'll get started with those. Let's see. JH is asking, do you also use Plotly? Not too much. I've played with it a little bit. I've never felt the need to use it because I tend not to do also very interactive visualizations. My plots are typically for print, so for a magazine or a static picture on the website. So I don't necessarily typically use interactive visualizations. And MP is still seems like it's still having some issues with the screen. So if you don't see what I'm sharing, you should just refresh your browser. That usually fixes it. It's probably some type of glitch with the connection. QN is asking, how can at 500 the blue is perceived to be highest? I'm guessing you're talking about this specific plot. No, at 500 the blue would be the shortest, so it would be the lowest one, the lowest intensity perceived. So maybe I misspoke or didn't make myself clear when I was explaining that. SS is asking, when the RGB intensity is changed, as I superimposes the wavelengths or perceives RGB components separately. So when you're changing actually going back to the same plot, so when you're changing the intensities, that's the same thing as you changing the wavelength that you're receiving, right? So think of it as your eye as being a black box, right? So it's something that works in a specific way. And your eye receives the light, processes it, and sends out nerve signals to the brain. These nerve signals are basically saying, what's the intensity that my red cones are seeing? What's the intensity my green cones are seeing? What's the intensity my blue cones are seeing? And what's the intensity of my rods? Right? So whatever light input generates the same intensity on the red, green, blue cones and the rods will result in the same output, right? Your brain will see no difference. So what that means is that by simply changing the intensities of the different components, what you're effectively changing what I'm seeing. Right? That's why with LCDs, it's very hard to see at this point. But if you ever had one of those old CRT TVs, like the big old clunky ones, if you look very, very closely, you can see that each pixel is actually 3 little lights, a red light, a blue light, and a green light. And depending on what the image is, the intensities of those lights are changing very quickly, right? And it's that change of intensity that makes you perceive the different colors that you're seeing. Even though the lights can only do 3 colors. SS is asking, why is the eye perceiving some colors as warm and some as cold? Essentially because they're associated with warm things and cold things, right? Fire is warm, is hot. So red, yellow, orange are the colors of fire, so you associate them with warmth. Ice tends to be blue or very light, or a purplish, or when you're very cold, your hands start turning purple. So those colors will be associated with cold. So it's kind of it's not so much that your eye is perceiving them as warm or blue, it's just the associations that you have with those colors. And another question from SS is when to use color schemes. So basically every single time you plot something, you're choosing the colors you're plotting it in. So you're choosing your color scheme. What I'm saying is you should be careful in the way you choose them, because that will impact how things will be perceived, right? You can choose the colors in a way that helps people understand what you're saying and helps transmit your message and makes it easier for people to decode your message in a sense, or you can use colors that makes it harder for them to understand it. Right? So that's why you should be careful. CR is asking, do you have suggestions for choosing colors for dashboard elements? So I can't give you a generic answer for this. What I can say is, depending on what you're doing, you will choose different color schemes, right? If you're doing a dashboard for a company, you'll probably have to use whatever color scheme that company uses, right? They will give you a color scheme and say, I don't know, AT&T, for example, tends to use blues, right? Different shades of blue, so you'll probably have to focus a lot on blues and so on. If you're doing something from scratch, it depends again on what message you're trying to transmit, right? Are you trying to give a warmer feeling? Maybe you should focus more on the yellows and the reds. If you're giving it a more cold or serious feeling, then maybe more blues and so on. So it depends a lot on what the message is you're trying to transmit. My recommendations would be choose the colors to be contrasting or similar, etc., depending on if you're trying to contrast something or highlight something and so on. And SS is asking, what is absorbance by the human eye? What does absorbance means? It's basically what fraction of the light gets absorbed. Right? So that, I mean, it's as simple as that. So here in this plot, 100% just means that all the light that gets received at that wavelength gets absorbed by the eye, while for smaller wavelengths, for instance, I'm looking at the blue line, for wavelengths, say, of like 350, only about 50% of the light actually gets perceived. So you see it as, even though you're receiving the same amount of light, the same number of photons, it seems darker than if it's 350 nanometers versus if it's 420 nanometers. So there's no more questions. Yes. So let's get started with the second part. Now we're actually going to look at visualizations and how to put together visualizations. Excuse me. So now that we understand a little bit how the human eye processes colors and shapes and areas and so on, we can start thinking about how can we use these tools to build up visualizations and to design our visualizations. One of my favorite books on visualization is this one called Beautiful Evidence by Edward Tufte, and where essentially he highlights 6 fundamental principles of analytical design. So 6 rules of thumb, let's say, on how to build up a design, how to design a visualization. And the way he puts it is that first, what you want to show comparisons and to highlight the contrasts and the differences, right? So you're trying to show what is similar and what is different, right? Because usually it's what's different that's interesting in some way. You also want, whenever possible, to show causality, right? To explain something or to show what the structure of some data is. Right? You want to use multivariate data, so you want to encode things in multiple ways, even if you can. So not only just colors and shapes, but also strokes, symbols, text, and so on. You also should integrate words and numbers and images. So that means putting little labels on things, highlighting specific points with little text bubbles and so on. Documentation. So this is very important. The figure, the visualization by itself should be roughly self-contained. So it should kind of explain what it's about. And it should be clear from looking at it. And this includes things like access labels, legends, annotations, and so on. But you should be able to understand what what the content is and what the figure is talking about. And finally, content matters most of all, right? If your data is very messy, it will be hard to get a clean visualization. And if your data is not interesting, again, it will be very hard to get an interesting visualization. So you can't show what you don't have, in a sense. And David McCandless actually put this, and this kind of became my, let's say, visualization philosophy, to kind of try to highlight in this first half or so of the lecture, is that information visualization is a form of knowledge compression, right? You're trying to get all the information you have on your data and put it in a representation in a format that takes advantage of how fast your brain is able to process visual information to absorb as much information as possible, right? To transmit as much information as possible. So to give you a very nice example, so here is one of my favorite visualizations from the New York Times a few years ago. And it's basically showing you the number of war casualties and civilian casualties in the Iraq war. Here they do something a bit unusual. They make the y-axis point down instead of up, which is a bit unusual or even a bit controversial, let's say. The reason they did that is because they colored the bars representing the number of casualties per day or per month in red. So you kind of have this perception, this idea, this visual representation of blood dripping, right? So you can see the deadlier months are kind of where you have more blood, the less deadly months, or even less deadly years where you have less blood. So kind of in giving you this visceral reaction to it. So it's taking advantage of your biases again in the way you perceive things to transmit the image and the idea that this is something particularly bad. So it's representing death. But not only that, this is also a very good representation of the principles I was discussing, right? So it has a clear title that says what this is. You have many annotations for specific points of interest with little text snippets in all the white space that's left vacant from the main plot, the main bar plot. You have other subplots that help explain what the story of the image is. You have what are the biggest regions where the largest number of fatalities have occurred. You have another timeline representation of the number of soldiers, some comments, some legends, and so on. So you can see how this image, in a sense, is a good representation. It's showing you a good image and a good view of what the message is, of what the data is, right? And just by looking at it, you see immediately many different things, and you get a very clear picture of what's happening, even though it's technically breaking the rule of always having the y-axis pointing up, right? So here you have the y-axis pointing down. On the other hand, you can just naturally break rules. So here you have a quick plot of survey answers to whether or not truncating the y-axis is dishonest. And if you just look at this, it seems like the number of people who answered yes and number of people who answered no is roughly the same until you actually pay attention to what the y-axis bar is. And then you see that there's actually a huge difference, right? So you can see that yes is actually 95% and no is actually 5%. Right? So, and what that means is that simply by the way you're representing things, right, you are impacting the way things are perceived. If someone is not paying attention, they'll read the question on top, they'll see the two large equal-sized areas and assume that it's a 50-50 thing, even though they're very different, right? So the way you encode things has an impact on how they are perceived. So, and this kind of brings us to the idea that there are certain fundamental tools, so fundamental building blocks of visualizations that you put together to build up what your story is, what your picture is, right? These are relatively simple things that you're familiar with, and depending on how you combine them, you will get very different results. Right? And of course, each result will be particularly suited for one purpose versus another. Right? And you can use these as a way of encoding features or variables of your data to transmit the right idea. And so the simplest one that you're probably most familiar with is the Scatterplot, where you just have points or perhaps even a trend line to represent a simple relationship between the y-axis and the x-axis. Another one is a bar chart, and here you're using essentially lengths and areas to represent the data. This is why you shouldn't truncate the y-axis in bar charts, because then you're shifting, you're changing the area that you're representing, and the area is what encoding your information. Bubble charts are actually very nice, and they're a little bit more sophisticated. We'll make one of these. Actually, we'll make this one specifically in a bit. And essentially what it does is it starts with a scatter plot where you have points relating the x-axis and the y-axis, but you're adding more dimensions, right? So you're adding size to the points. So now instead of having simple points, you have circles, and the area of the circle is encoding some information. You can add color as well. So different points will have a different color representing some other variable. In this case, the different colors correspond to what the continent is. You can even add a fifth dimension, which would be time, where you make the picture change over time. So you animate it and so on. So you can see how even with very simple tools, you can start building up fairly sophisticated things simply by combining them in smart ways. So with pie charts, what you're using are essentially areas, angles, and colors. Again, we've seen why you should, in most cases, you should try to avoid using angles to distinguish things, but sometimes they can be useful. You can also have heat maps, and here you're just using colors to represent differences from one part of the image to the other. So this is a population map of the US. So darker colors means less population, lighter colors mean larger population within each cell. And I've added also a very rough view of of a map of the state boundaries as well. And we'll build up this picture in a second. So now let's see, do we have any more questions? So no more questions, that's good. So now we can start looking directly at matplotlib and how matplotlib can be used to build up our visualizations in any way you want, and you'll see how it's very, very flexible. Also because it's fairly low level, so you can build up anything from scratch, but on the other hand, you also have to build up everything from scratch. So matplotlib is a two-dimensional, mostly two-dimensional. You can also do some three-dimensional stuff. Plotting library. It gives you a very fine-grained control about all aspects of the figure. You can control everything. I particularly dislike most of the defaults it comes with, but again, it lets you change all the defaults, so it's not too bad in that sense. And like I said, it's the basis on which everything else is built up on top of. Right? So Pandas uses matplotlib, NetworkX uses matplotlib, Seaborn uses matplotlib, and so on. So here are some examples of some fancy things you can use to build up matplotlib. So this is from the official gallery of matplotlib, and actually, if you go on the website and you click on one of these images, you can actually see the code that's used to generate this. Right? So it gives you a nice way of learning how to build up very sophisticated things by showing you how different examples work. So let's get started with some fundamental ideas of plotting and how things are plotted. So we have the simplest possible plot is as I mentioned, it's the scatter plot. You have an x-axis and the y-axis. You have some points and maybe a line that shows you some trend or some average behavior. You have axis labels, you have markers or symbols, you have lines, you have text objects, even some annotations. And matplotlib uses essentially an object-oriented structure that uses the same notation, the same name. So it's a very intuitive thing. So you have axis object that represents essentially a subplot. Each axis can have an axis object. So I'll try to overemphasize the E and the I to make it clear if I'm referring to the subplot or to the individual axes. A figure, so the full figure, is one or more axes. So you can think of a figure as being one or more subplots. Most figures only have one subplot. Others can have many. Each axis, so each subplot, belongs to exactly one figure. Each set of markers belongs to exactly one axis, one subplot. So in a sense, the markers and the lines represent the data that's being plotted with respect to one specific set of axes. And the axis, as I mentioned, is a subplot. Right? So this figure is from the official matplotlib documentation and kind of highlights very, very clearly the names of different things. It makes it so I use this as a reference very, very often. So you can have also major ticks on the axis, minor ticks. You can have splines, you can have grids, and so on. Also tick labels, minor tick labels, and so on. The figure object, so it's the object that contains the whole figure that contains the other subplot figures, the other axis objects. You can always get what is the current axis that you're using by using GCA, so get current axis. .show is used to show the final figure. If you're using an interactive system like Jupyter Notebook, you usually don't need to explicitly do .show. It just does it automatically for you. If you're writing a script to run from the command line, then you probably have to do .show. Savefig allows you to save the figure in a set of file formats. It has a wide range of formats like JPEG, PNG, PDF, and so on. And it will automatically select the correct one by changing the file extension. So let's see how we can actually build some simple plots. So the first step is to import matplotlib. For historical reasons, you should do import matplotlib.pyplot as PLT. This is kind of the standard way of importing it, the conventional way. The axis object, as I mentioned, corresponds to a subplot. You can do fig.subplot or plt.subplots rather with a number of rows and a number of columns to say how many subplots you want. And if they should have a common range for the x and the y axis. Subplots will return both a figure object that allows you to control the figure itself and the list of axis objects. And then with the axis, you can plot the data directly. So the simplest way is just to axis.plot, and then you give it an x and y, and it'll give you a scatter plot. You can also give you a line plot and so on. emShow will plot a matrix of data, so a matrix of values, as if it was an image. Dot bar will give you a bar plot. Dot py will give you a py plot. And as we saw already, savefig will write the figure to a static image on disk. As you saw, there's many other things you can do to customize the aspect, the feeling of your figure. You can set X labels and Y labels, so labels for the axes. You can set a title for the entire figure. You can define the range of the axes if you want, using set xlim and set ylim. Excuse me. You can manually specify where the tick marks and the tick labels should be. And this will come in handy when you're trying to do something particularly customized. And finally, like I said, plt.imageShow will display the image. We'll add an image to a specific figure. You can also define exactly where within an axis or within a subplot that figure should be. So you can add little pictures as annotations even to the general subplot. And you can keep stacking these things on top of one another by simply adding them and calling the same method multiple times. And multiple data would add, for instance, different lines, different points, and so on. So before we jump to the notebook, we have a few questions. SS is asking, it looks like there are 30 visualization libraries in Python. Any tips on how to pick for given visualization requirements if you could choose from it? So, yes, so there's many visualization packages. Like I said, they all build up on matplotlib, essentially. But typically you have two classes of packages. You have static packages, let's say, and interactive packages. And static packages all build up one way or another on matplotlib. Interactive packages typically rely on JavaScript to some degree to build up some type of interactive image that you can click on things and change and add to a web page and so on. I'm not as familiar, like I said, I don't really use those things, so I'm not as familiar with them. I know things like I've played with things like bokeh that allows you to do actually relatively sophisticated plots very easily. Let me actually find the link for this. And you can, I'll put it in the group chat so that everybody can find it. And this will give you some very nice interactive visualizations. For static visualizations, I would recommend matplotlib and Seaborn. Pandas will also let you do some quick plots, but again, building up on top of matplotlib. But for quick exploration of your data, that's perfectly fine. If you want to do something more sophisticated, I would probably start either with a package that already has, that makes it easier for you to do a specific visualization if that's what you want, and that builds up on top of matplotlib so that then you can customize it afterwards. DG is asking, does axis equal subplot? Yes. So an axis object with an E is exactly a subplot in the figure. JH is asking, what are splines? Oh, splines are just lines. Right? I mean, the visualization package doesn't care where the line is coming from. It's just a line. SS is asking, in the same subplot, I want to draw multiple visualizations, how to do it. As I said, you can just call the functions, as long as you keep calling functions like plots or bars or so on, they will keep getting added to the same subplot. So I'll show you in a second how to do that. SK is asking, can you have an example for axes plot? Yes. Yeah, I mean, I'll jump now into the Jupyter notebook, and I will give you plenty of it. So basically, all the figures I've shown you in the slides so far, almost all of them, I will show you how to make them yourself. Right? So you will see the code and how it works and how the different pieces relate to one another. And JV is asking, polar bar use angles and bars. Seems combine pine and bar charts. Still, bar charts can be better due to the reference to the axis and spaces along the axis. Matplotlib, I don't really use polar coordinates, but Matplotlib will let you do that actually. So let me find you the right representation. So maybe I should actually add an example on that. Give me 1 second. So you can do yeah, so here is, again, I'll put it in the group chat, just make it easier. But basically there are specific functions to build polar charts, right? And they're very flexible. You can do almost anything you want, just using a different set of coordinates, essentially. Let's see, do I have any more questions? So no more questions. So now let's jump to actual code so I can actually see how these things work in practice. So let me start sharing my screen. So you should be seeing my my browser now. So this I'm showing you also what I have in the GitHub repository. So you can see you have all the notebooks. Inside the slides folder, there's also the PDF version. Actually, I should update that. I've updated the slides a few days ago. So I'll make sure to push the new slide version after in the next break. And also you have, like I said, all the notebooks that help you, that show you how to generate all the figures I'm using. Now, you can also, like I mentioned, register for the newsletter. The last one, the most recent one just went out yesterday. So let's get started. So there are 4 notebooks in the repository. I'm going to start with the first one, Matplotlib. My notebooks all follow a similar structure. So I always import all the modules and packages I'm going to use right at the beginning. So this has the advantage that if you're missing a package, if you don't have it installed, you'll find out immediately. I try to use as much as possible relatively standard things. So you'll see that I'm essentially just using Matplotlib, NumPy, and Pandas. The only non-standard thing I'm using here is watermark, and this is not terribly important. You can just comment it out if you don't have it. And the only thing watermark does is it allows me to do this, where it's essentially checking all the packages I have loaded in memory and telling me exactly what the versions are that I'm using. It's also telling you exactly what version of Python I'm using, what version of IPython or Jupyter Notebook, what my machine is, what branch of the GitHub of the Git repository I'm using, and so on. So this essentially makes it very easy for you to check that you have the same setup as I do. So if you have any problems and the code doesn't run, you can see if it maybe because you have an older version of some library and so on. But like I said, if you don't have watermark installed, that's fine. You can just comment it out and not run this line, and everything else should work just fine. This is a little bit of magic that I will explain later, but essentially it's making the default figure size larger. So you start with with a basic plot. Here I'm just using NumPy to get some fake data. So I'm generating some point between 0 and 2 pi, and then I'm calculating the sign of those values. And as you said, for something very simple, you can just do plot xy, and that will plot it. So actually, let's do that. Plot xy by default will give you a line. If you put a little star there, then it will give you a simple scatterplot. You can also use other symbols. This. And if you want to make it explicit that you want a line, then you put a little dash there. You can also specify what the color is. So in this case, I'm plotting X and Y in red. Matplotlib knows the name of some colors, but not that many. And of course, you can also add legends and so on. Actually, one thing to keep in mind is that until you close the image, so typically if you're doing a script, this would be up to the point where you do plt.show. All the commands you run will keep adding things to the figure, right? So you can just add new things. In this case, because I'm using Matplotlib, or rather, if I'm using Jupyter will do that for me, so I don't have to keep writing plt.show. Right? So I can just do this, and now if I want to add a legend that says sign function, then I can just do that. And like I said, if you want to plot multiple things, you can just call plot multiple times. Right? So here I'm plotting the data both as a red line and as blue stars. So, and you can imagine this being where the star, the scatter plot, are representing the actual data points. The line is a fit or some reference line. And of course, you can add the legend for both elements of the figure as well. So now we're going to build up the different plots we saw before. I have a few small data files I'm going to use in the data repository. And this is a little data set. And here I'm just using pandas to read the CSV file in a simple way. And this little data set is basically a marriage data set that basically lists for about 170 couples the age of the wife and the husband when they got married. Right? So you can kind of see the relationship between husband and wife, in age difference between husband and wife. So you can build a scatter plot by simply saying what the x-axis is, what the y-axis is. You set the x label and the y label. And then in this case, I'm even saving the figure as a PNG to disk. So it takes a couple of seconds. There you go. You can see how you have all the points. You have the wife age on the x-axis. You have the husband age on the y-axis, and so on. And if you look in your disk, you now have a figure, an image, a PNG file with the actual figure that looks exactly like this. Actually, I can show you that. So I can go here, and now it's here, ages.png. So this is the figure I just generated. As I mentioned, pandas also lets you generate plots simple plots very easily. So you can just say ages.plot.scatter and then say what you want for the x-axis and for the y-axis. And one thing to keep in mind here is that this actually generates a matplotlib axis. And so what this is returning is the axis object. So it's kind of the subplot object that you could then use to modify the figure. Right? So here I'm doing the same thing as before. So you'll see that this line is exactly the same as that one. I could simply do here this, and this would still work. Here I'm doing it explicitly just to show you how you can always get what the current axis is in a simple way. So this just means PLT, so matplotlib get current axis, GCA. And now I can use this axis, so this is axis with an E, or rather axis with an I, object to set specific the label for the x-axis, the label for the y-axis, the title for the figure, and so on. So here I'm, instead of keeping the default column names for the x and the y-axis, I'm actually specifying that I want the X label to be wife's age, the Y label to be husband's age, and the title for the full figure to be age at marriage. And now if you want to add, you can, like I said, you can keep adding things. So on top of all of that, I can now add also another plot with the red line that represents the fit to the data. And even the legend that tells me what the fit is and what the data is. So you can see how it's easy to combine all these simple pieces and to start building up something fairly sophisticated. So now you can look at the bar plot. So here I'm just making up some fake data for LA and San Francisco, say. And now we start looking at how to build up a more sophisticated plot in a relatively simple way. Right? So we create a new figure with one subplot. So this will return me a figure object and an axis object. I'm manually setting here the figure size to be 14 inches by 10 inches. So this is width and height. And now I'm adding two bar plots to the figure. One bar will be the data for LA. One set of bars will be the data for San Francisco. I'm specifying how wide I want the bars to be and what the labels are, and also where I want the bars to be located. So you'll see here that I'm defining the positions for the bars as being range between 0 and 5 with steps of 2, so it will be 0, 2, and 4. And the width of the bars, 0.5. So this gives me a lot of control on whether I want the bars touching each other, if I want a little gap between them, and so on. So let's do that. So this is what you would get. I could, for instance, do something like this. And now I'm adding a little gap between the two bars and so on. As before, I'm setting the X label and the Y label. I'm manually also setting the ticks and the tick labels. And this is because I want, let's do this again. I want the ticks to be exactly in between the two bars. So that's why I'm setting them to be at position plus width over 2. So pause here will be the left corner of the bar. And then, of course, also the labels for each of the ticks as being A, B, and C. So you can see how you're starting to make a nice looking figure by gradually, step by step, adding the different pieces together. You can also build up a pie plot. I've mentioned already, you should be careful when using these. They're not particularly good plots to transmit to make comparisons between values unless the values are very different. So here you can see how it's hard to distinguish the different widths of the different bars. For example, just by looking at the figure, I would have a hard time saying, if without the value labels, I have a hard time saying whether the green bar or the orange bar, which one of them is larger. This, of course, is very different if one of the bars, for instance, like this, is much larger. Right? And then you're trying to emphasize how big this one is with respect to the other ones. Right? And there it works a little bit better. And to make the little comparison between the pie plots and the bar plots, as I showed you in the figure, and this is also acts as a nice way of showing you how you can have different subplots in the same figure, right? So here I'm just getting the list of, manually getting the list of colors that Matplotlib is using. And this is just so I can force the colors to match between the different subplots. And so you can see it here, I'm using subplots, and I'm telling it I want 2 rows and 3 columns. And this will return a figure object and also a list of axis objects. And here the list, because you have 2 rows and 2 columns, will actually be a list of lists, where so it will kind of be represented as a matrix, and you can index the position you want directly. So 0, 0 will be the top left-hand corner, 1, 2 will be the bottom right-hand corner. So on the top row, so row 0, I'm setting the different pie charts. So here using data A, B, and C, and setting the labels. and then for the bottom row, I'm setting the bar chart with the same data. Because, let me show you how this works. Yeah. Because I'm putting the bars side by side, so I want to, so in a sense, I will naturally compare them. So the blue bar here with the blue bar here and the blue bar there. I'm also manually forcing each bar plot to have the same Y scale, to have the same Y range. If I don't do that, here, you will see how, for instance, on this side, the range on the Y-axis goes to 25. Here it only goes to 20, and here it goes back to 25. So it looks like this bar is almost as large as this one, even though they have very different values, right? So whenever you have plots like this that are side by side, you should, especially if they look very similar to this, you should always use the same scale for the Y-axis, right? So and that's what I'm doing here. And now it becomes clear that this is the smallest blue bar, this is the intermediate one, and this is the largest one. And here, because I want the colors of these bars to match the color of the slices of the pie, I'm manually setting the colors for the bars. So that's why over here, I got the list of colors, which is just the default list of colors that Matplotlib uses. And here I use that and to tell it to manually set the colors. Otherwise, if I don't do this, it will plot all the bars in the same color. Another way of obtaining the same result would be to plot one bar at a time and say, okay, I want this bar with this height at this position, this height at this position, and so on. And then it would naturally cycle over the same set of colors. Because I'm lazy and I didn't want to write 15 lines just doing the same thing, I just set the colors for each bar manually. Now, patches, so we've seen how we can do lines and symbols and bars and pies, but we can also do patches. So patches are basically shapes, right, In this case, I'm going to be using rectangles. And they're going to build up this little optical illusion that I've shown you. And what this has essentially are a bunch of horizontal gray lines and rectangles. And the position of the rectangles is changing from one row to the other with a sine wave pattern. So this is what we're doing. So I'm getting a new figure. I'm getting a handle for the axis object. So this is just an equivalent way. I could have done this exactly the same this way. These two lines and this line are exactly equivalent. I did it this way again to illustrate a different way of doing it, just so we can have kind of a different repertoire of possibilities, even when they are more or less equivalent. My squares list here is where I'm going to put all my rectangles. And I'm going to do 8 rows. For each row, I'm going to plot the horizontal gray line. So you can see that it starts at x equals 0. It goes until x equals 25. And the y value is just 0, 1, 2, and so on for each row. So you get this line, and then this line, and then that one, and so on. And then for each row, I'm generating the set of rectangles that I'm going to be adding. Each rectangle has width of 1 and a height of 1, and will be filled with a color. And the position will be given, like I said, by a sine wave that's based on the row. So here I represents the row, J represents the column. And will be at the corresponding row height. And now, after I generate my square, I add it to my list of squares. After I do this, so I've essentially added all my lines, I've created all my rectangles or squares. I'm creating what's known as a patch collection of squares. So this is how you add the patches to the plot. You don't actually add one by one. You create a collection of patches. You define what the colors are that you're going to be using. Here, I only set one color, so we'll use the same color for all the rectangles. I could have given it a list of colors, and then that would set the color for each rectangle or each square separately. And then after you have the patch collection, you just do x.addCollection, PC, and that will essentially draw all the squares. Finally, axis off essentially removes the x and the y axis from the figure, and tight layout basically tells Matplotlib to remove any extraneous white space that's not being used. So when you do this, this is the figure you end up with, as we expected. And just so to make it clear, if I don't those, then you just get a normal figure as before, where you have the y-axis, the x-axis, and all the tick marks and so on. So with axis off, I remove the box essentially around the plot, and all the tick marks and so on. And with tight layout, I reduce also the white space. So I'm using as much space for my plot as possible. Excuse me. Next, we move on to the bubble plot. As we saw, the bubble plot is kind of building up on the idea of the scatterplot by adding extra dimensions. Now I'm going to use data from Gapminder. And if you've never heard of Gapminder, you should definitely check it out. It's an awesome website that visualizes human development data from around the world and helps us contrast and compare countries in different parts of the world over time, which is amazing. I'm going to define also, just for ease of reference, a range of colors. So this would be the color scheme I'm going to be using. and also a list of continents. The data that I have, so the CSV file that I loaded has a country name, the GDP of that country, the population, the life expectancy, and the continent. So continent 0 is Africa, continent 1 is the Americas, continent 2 is Asia, and so on. And what I'm going to do is I'm basically going to encode all of these different features, or these different data values as different in different ways so that I can combine all of them in the same plot. Right? So here I'm going to set GDP to be on the x-axis using a log scale. Life expectancy will be on the y-axis with a linear scale. Let's make that clear. The population will be represented as the bubble size, so it will be given by the area. And finally, the continent will be represented as the color. And finally, I'm using also ax.text as a way of adding text to the figure. In this case, the text I'm adding is simply the name of the continents with the right color, right? So that acts as a legend. So again, I'm creating a figure and the axis object. I'm setting the figure size. And then for each continent, and so I have 5 continents, 0, 1, 2, 3, 4. I'm selecting the data for the countries just on that continent. And I'm creating a scatterplot. So I'm adding a scatterplot to the figure where I'm plotting the GDP on the x-axis and the life expectancy on the y-axis. I'm scaling the area of the bubble to be proportional to the population. And here I'm just dividing by some large number, just so the bubble is not too large. I'm setting the colors to use, and alpha basically gives me the transparency. So 50% transparent to make it easier to see when bubbles overlap other bubbles. I'm setting the scale on the x-axis to be logarithmic. And finally, I'm adding the legend, so the name of the continents with the right colors, by specifying the x and y coordinates of where I want to draw the text. Right? So here I'm setting the text to be at coordinate x equals 300 and y starting at 83 and then 81, 79, 77, and then 75. And then writing the name of the country in the corresponding color. So this will be my kind of my legend. Right? Finally, I'm setting the X label and the Y label. It's always important to label your axes. And finally, I'm telling it to give me a tight layout, so to remove any extraneous white space, unused space that you might have around the figure. And so you can see just by looking at the figure some very, very nice patterns. For instance, as you increase the GDP per capita, so as you're moving right on the x-axis, you're also moving up on the y-axis. So richer countries tend to live longer. The colors also give you interesting information. So you can see, for instance, that African countries tend to be poorer and live shorter lives. You can see that you have two very large countries, or two countries with very large populations in Asia. So this, of course, would be China and India. You can see how these lime green little circles tend to have smaller populations but be very rich and live very long. So these are the European countries and even most American countries. So this large bubble, pinkish bubble over here is the US with the largest population, and so on. So you can see how this simple figure is encoding a lot of information, right? And it's already giving you a very nice picture of this data set that actually has many different features and that are used to convey a very important message. This could be made even more impressive, and this is one of the things they do in the Gapminder website, by showing and animating this plot as a function of time. So where each frame, for example, would be a different year, and you can see how the different countries are moving over time, both on the x-axis and on the y-axis. So countries overall tendentially get richer over time, and the life expectancy tends to increase over time. So we can see how, in a sense, inequality across countries has decreased as we progressed in the last 40, 50, 60 years. Another interesting plot that's pretty common, especially if you do some type of demographic research or use census data, is the age pyramid. So this is kind of a way of summarizing how many men and women you have in each age group. So I downloaded some age pyramid for Mombasa in India from this website. And essentially what we have is that for each age group, so from 0 to 10, 10 to 20, and so on, for male, how many males and how many females you have, and some other information. So I'm going to build up this plot in exactly the same way. So now I'm using subplots directly. So I'm getting a figure and a set of axes. My plot's going to have one row and two columns. And I'm not sharing the X and Y scales. I'm plotting my data as horizontal bars. So you saw before the dot bar method. Here, bar age is the same thing, but it represents the bars horizontally. So here, instead of being the X coordinates, would be the Y coordinates, and then the corresponding values. So I want to match, I want to make sure that the same age group for males and females is represented in the same location. For the left-hand plot, I also want to invert the x-axis. That gives it this distinct look of where you have bars pointing out from a common center. That's why it's called the age pyramid. I'm also removing the ticks and the tick labels from the left-hand plot, and I'm keeping just the ones on the right-hand side. I'm manually setting the tick positions and tick labels on the right-hand plot to be the age groups. So, but here, I mean, I could have set anything I wanted. And any list of strings would have worked. In this case, I'm taking advantage of the fact that my data set already has nice labels. Setting the X label for the X-axis for both subplots. And finally, I'm adjusting. So this is a relatively fancy thing that you don't use very often, so I actually had to look it up. I'm basically specifying how much space I want between the two plots. Right? So how far apart do I want them from each other? And so I kept them, so I set it to trial and error, essentially, through 0.18, so that they would be more or less centered around the labels of that I'm using for the different age groups. So when you do this, you get this nice representation. It actually works pretty nicely, conveys this picture of the age pyramid. Right? So you have, depending on which country you are, you tend to have either very large values of children, so very large numbers of children, so 10 years from 0 to 10 and 10 to 20 years, and then the numbers decreasing as you go up. In other countries, for instance, in Japan, that don't have, or even China more recently, that don't have as many children and that are starting to have an aging population, you would actually have what's called an inverted age pyramid, where you have a lot of elderly people and very few children. So where this picture kind of look upside down in a sense. Another interesting plot you're likely to have encountered, especially if you look at the stock market, is the candlestick. And this is basically summarizing, again, a large amount of information in a very condensed way. So here I'm getting the value of the Dow Jones Industrial Average over the course of several years. So I downloaded from Yahoo Finance. So if you click on this link, you can download an updated version if you want. I'm selecting here just the last 52 weeks. Just to make the chart more readable. And finally, what I have in the data set is basically the date. So this is the date of the Friday of that week. What was the opening value of that week? So what was the first value on Monday? What was the highest value it saw throughout the week? The lowest value it saw throughout the week? The final value. So this is the final value at the end of business on Friday. The adjusted close is if there was some change in this value due to trades that happened after hours. And then finally, volume is just how many stocks were actually bought and sold. And what we're going to do is we're going to grab all of this information and we're going to put it all in a single plot that you can read very easily and very quickly. Right? In particular, I'm going to use the opening value, the close value, the highs, and the lows. Here I'm just splitting it off into different series just to make it easier. The change is the difference between the closes and the opens. Right? So if it, oops, I need to actually run this, and then I can run this. So this basically tells me did the price increase or the price decrease. And this will give me a Boolean vector that tells me when the changes were positive. So when the price increased, and the downs will give me the list of all the position of the times when the price decreased. I'm also manually specifying what the position of the bars is. So the 0, 1, 2, and so on. And what we want, so this is what the final result will look like, is for each week, we'll have one bar and one line. The bar will be colored red if overall the price went down. So if the close is smaller than the open, and it will be colored green if the close is higher than the open. And that the open and the close are kind of represented by the size of the bar. And the size of the line that's on top of the bar tells me what is the variation of the prices. So the highest price and the smallest price. So you can see how easy this is to do. So I'm essentially have two bar plots. I'm going to use one to plot the green bars and one to plot the red bars. So I'm selecting here the positions for all the times the price went up and the position for all the times the price went down, the corresponding height. So this is the size of the bar. And in the bottom here, I'm specifying where I want the bar to be plotted, right? So by default, with bar plots, the bottom is 0. So it starts plotting it at 0. This is not what we want. What I want here is to start the bottom to be the minimum value and then to draw the bar from there, right? So that the bars kind of move up and down as well. So you can see that nicely here. And this final plot here, call to plot here, is drawing all the vertical gray lines. And this is doing it in a fancy way because I generated these two essentially lists of values. So it has 2 rows and 52 columns for Y and 2 rows and 52 columns for X that basically plot interprets as being separate lines. So you can plot many different lines in a simple way. Actually, let me show you what this looks like. oops, yeah, because I didn't actually run this. Sorry. Yeah, I need to. There we go. I forgot a bunch of stuff. So you can see how this is one of the rows. This is the other row. And this is essentially draw a line between this value on Y to this value on X, and on Y, and so on, while keeping the X value fixed at the position there. So you can see it has 2 rows, 52 columns. So with a single line of code, I can add all of the different vertical lines. Here, the Z order, so this is an interesting parameter, it basically tells you how the different things should stack on top of one another. Right? So you can imagine the plot to be a stack of different plot elements, right? So kind of like a stack of playing cards. The bottom layer is Z order 0, the one on top of that is Z order 1, and on top of that Z order 2. By default, the order in which things will be plotted will be the order in which you call these functions. Here I explicitly wanted to use Z order to make it clear what I'm doing. So here I'm plotting the bars in Z order 2, so layer 2, and I'm plotting the lines on Z order 1, so layer 1, so below the bars. Right? So I explicitly made it this way so to illustrate what the Z order parameter does, and this is why you don't see the bar on top, or the line on top of the bar, but it's actually hidden by the bar partially. And then finally, I'm setting the tick marks and the tick labels. And I'm doing it just once every 4 weeks, so it kind of represents what the month is. And the rotation equals 90 means that I'm writing the label this way, so perpendicular instead of parallel to the axis. And then finally, the X label and the Y label that gives me this final plot. So you can see how a simple plot can actually convey and include a lot of information, and you can see very, very clearly trends, for example, where from this week here all the way up to this week, the trend was going up, then it kind of went down for a couple of weeks, and so on. You can also see how some weeks, for example, have much larger fluctuations, so much larger variations between the high and the low. For instance, like in these 2 weeks here, in this case, you have a very large variation between highs and lows, but also relatively large variation between opens and closes. And here you have just a huge variation between highs and lows, but a tiny variation between opens and closes, right? So the bar is very small, but the line is very large. And finally, you can look at images. So IMRead allows you to read a file, an image file from disk. You can just plot it with IMShow. So this picture is in the data folder as well. And the picture essentially, as far as the computer is concerned, is a stack of 3 matrices, where each matrix represents a color component for each of the pixels. So we have here 2048 pixels height, 1371 pixel width, and 3 color components, which of course will be R, G, and B. And image show, of course, is smart enough to interpret this and to show the colors directly. You can also plot out the different components separately. So here I'm just subsetting component 0, component 1, component 2, and plotting them as different subplots. So using, again, subplots, 1 row, 3 columns. And I'm setting all the axes off so I can see how the pictures look without all the annotations around it. And of course, I can also add this. Yeah, and you can see how that moved the pictures a bit closer and made them a little bit bigger because there was empty space that it could be reused. You can also use this as a way of visualizing color gradients if you want for the different color maps. So here I'm using the Viridi's color map. So that you can see how the color is the spectrum in this color map is changing. And because pictures are just arrays of numbers, we can manipulate them just as we would use any other matrix or any other array. And this is how we're going to be simulating the different color blindness types. So I stole these matrix values from this website, right, from this JavaScript library. So that I can generate this figure here, basically illustrating how the different vision types will perceive the same image differently. And the way this is done is, so I create a subplot of 3 by 3 figures. I'm sharing the X and the Y axis. I'm getting the names for all the different types of vision. So I'm just grabbing the keys from this dictionary. And then for each of them, I'm getting the name, getting the corresponding transformation matrix. So these matrix here. I'm grabbing my original image. I'm reshaping it to be, instead of a three-dimensional value, I'm flattening it out so that it's a long line of pixels, and for each pixel I have the 3 color components, and that means after I do that I can just multiply each value by the transformation matrix to get the new pixel value, and then convert it back to an image type, which I can then reshape back into the original image shape and plot it in the right location. And its row and call is just calculating exactly where the picture should go, what axis value it should use, setting the correct title and removing the axis. Here again, I'm adjusting by hand the spacing, the horizontal and the vertical spacing of the different images, and then adding the title layout later on. So this will take a couple of seconds because it's doing a lot of stuff, but you'll see how it's generating exactly the same image as before. And of course, you can easily just load up here. If you change the image that you're loading here, of course, you will see a different image here. So I use this sometimes to check if my visualization pictures are actually visible and perceivable with the different color blindnesses as well. So let's go back, see if we have any questions. So there's no questions right now that I can see. Yeah, so no questions on the Q&A widget. Let me check quickly the group chat. Ines is asking, is it possible to get tick marks only for the left graph in the H pyramid? Yes, so you basically actually I can show you that. So let's go back to screen sharing. So here, where is, yeah. So here I'm removing the tick labels and the tick marks on the left axis. I could have done the same thing and remove them for the right figure. And then setting them here. This is the same thing, but now you see it ends up on the other side, right? Because the y-axis is always, the ticks and the labels are always on the left-hand side. That's why I chose to put them only on the right hand plot, because that way they would be in between the two figures. So it's a more natural way. And then C is asking, fig variable is used for global settings. Yes, so it's used basically to change the settings of the figure as a whole, right? While the AX variables usually are used to modify the settings for a specific subplot. So we have a few more plots, a few more questions. JC is asking, how do you plot on the secondary y-axis? You can, wait, let me see. You can create a secondary y-axis and actually plot things side by side. And you do this by creating a twin X or a twin Y plot. So this is I don't have any example in the notebooks, but I'm putting in the group chat the link for the documentation for how to use different scales together. Let's see, have any more questions? SS is asking, what does the pyramid visualization convey? Oh, so this is a way of showing the age structure of a country or a city. So it's a way of representing how many males or many females you have in different age groups. So this is a traditional visualization for demographics, census information, and so on. And SS is asking, what is the purpose of VStack and HStack and how to use them? Oh, so VStack and HStack basically just put the vectors on top of each other. Right? So you can stack them as being rows, so each vector is a row, or you can stack them as being columns, so each vector is a column. So it's just a way of combining vectors in different ways. So it's a standard NumPy, they're standard NumPy functions. And SS is also asking, is it possible to change the font size and the color of the axis labels? Yes, and it's actually, I should have mentioned that. It's actually surprisingly simple. 1 second. So you can do something like this. So you can set the font size manually if you want. By default, I mean, Matplotlib uses a bunch of defaults, so it sets all the font sizes automatically for you. But if you want to modify them and make them bigger, there's nothing stopping you. And sometimes I would do that actually. I want to make something particularly clear or bring attention to something. Actually, I should probably make it here. Yeah. And you can even specify the font and so on. So now I've made my label font a bit larger. So this is usually works, and in anything that uses text, you can use font size. You can also, there's also font families, but that depends on which fonts you have installed on your system and so on. So it's a little bit trickier. Let's put this back. It was. Okay, so no